So, welcome back. At least half of you made it safely back from skiing. This morning I tried to give a more general introduction to the field of type 1a supernovae and how we attempt to model these astronomical objects in an astrophysics scenario as thermonuclear explosions of white dwarfs, and I gave some reasons why we believe that this is the right picture, why we think that type 1a supernovae can actually be described as thermonuclear explosions of compact objects of white dwarfs. So this is what we discussed, and we gave some reasons why this actually fits into the picture. Now in this afternoon lecture, I will do the second half of the introduction. And in this part, I will actually talk about why we're interested in type 1a supernovae, and then I will say some general remarks about the status of modeling and the modeling challenges in describing thermonuclear supernovae. Of course, if you give talks about type 1a supernovae, you always have to defend yourself and tell people why this is interesting. And usually people then say, well, this is interesting because type 1a supernovae are important for cosmology, and type 1a supernovae are important as sites for cosmic nucleosynthesis. But of course, what you should say first is that type 1a supernova research is important for understanding type 1a supernovae, and these are fascinating objects by themselves, and therefore, actually, I think one should take the courage and say, well, this is actually why we do it, because we're interested in the objects themselves. And indeed, they are interesting for a number of reasons. They are, as we saw this morning, extremely bright, and therefore they have received the attention of people in all over history, and there are lots of historic records of events on the sky that we nowadays associate with supernovae. They were early on realized as important astronomical events, and the observation characteristics actually make supernovae, in particular also type 1a supernovae, prime targets of astronomical observation. And this is because they are bright in the optical wavelengths. We discussed this morning that the emission is mainly of type 1a supernovae in the optical wavelengths, so one can see them, and they evolve on human timescales. So they are not objects that actually happen on milliseconds or something like that, but one can actually see them evolving over days, and this actually was accessible already to ancient astronomers, and this is why type 1a supernovae are important for the development of astronomy. So they played a fundamental role in establishing astronomy as a science. So the particular two supernovae that helped with making astronomy a science was certainly the supernova of 1572 that was observed in great detail by Tycho Brahe. He also coined, as you know, the word supernova or nova in this respect. Super was later added by Zwicky to distinguish them from classical novae. And this supernova, of which you see Tycho Brahe's finding chart here on the upper left, we know today was a type 1a supernova, and this can be actually reconstructed on the basis of light echoes, and from these light echoes one can actually extract an integrated spectrum, and this spectrum is prototypical for a type 1a supernova. So we're pretty sure that this was a type 1a supernova. The next supernova, galactic supernova that was observed was supernova 1604, that was then in greater detail observed by the successor of Tycho Brahe, by Johannes Kepler, and this probably also was a type 1a supernova. Now, Brahe's main work actually was on measuring distances to stellar objects and to stars and to planets, and he actually achieved very high precision positioning measurements of such objects. He could measure parallaxes very well, and for that actually he built new instruments. So this was all before the telescope was used in astronomy, but he already developed some instruments for measuring positions of stars, and he also came up with new methods of astronomical observations with different teams doing independent observations and then do blind test and this kind of stuff. So he actually sort of introduced quite a number of what we would nowadays call scientific methods to astronomy. Now, with these very precise measurements that he was able to do, he was able to, at least to the limits that he could detect, to exclude a parallax for supernova 1572. So therefore, by the picture people had back then, this was an event that took place in the sphere of fixed stars. Now this actually was quite a surprise, because according to the back then accepted Aristotelian world model, the sphere of fixed stars was immutable, so there were no changes allowed there. Changes were only expected on Earth and for the planets. But of course, obviously, supernova 1572 drastically changed its brightness, so therefore there was a change in the sphere of fixed stars, and this is actually what one could perhaps call the first cosmological revolution based on type 1a supernovae, because this actually then contributed significantly to the establishment of a new view of cosmology. Now, before we get to the second cosmological revolution based on type 1a supernovae, I would like to say some words about another aspects where type 1a supernovae are important for astrophysical processes, and this is the cosmic cycle of matter that you see here in the background. So the basic idea, of course, you probably know, is that we have the interstellar medium, and from overdense regions by collapse stars form, and then in these stars, under conditions of high temperatures and densities, the material gets processed in nuclear reactions, and in the end by stellar winds and by supernovae, this material is expelled or even further processed by the supernovae, and it's then expelled back into the interstellar medium, enriches the interstellar medium chemically, and out of this interstellar medium, chemically enriched interstellar medium, then the next generation of stars forms, and the cycle starts over, and this is how you could, in a very schematic way, picture galactic chemical evolution. So type 1a supernovae are actually part of this. They are the end stages of stellar evolution, so the end stage of the right-hand side of this cosmic cycle of matter, where the processing of the material in stars takes place, and they distribute then the material back into the interstellar medium by explosions with high ejector velocities, as we discussed this morning. They also drive shock waves into the interstellar medium, so they could actually also contribute to triggering star formation. Now, important are type 1a supernovae in this context because they are the main source of iron in the universe. So iron is what you could call the cosmic clock that measures the nucleosynthetic age of stellar objects, and it sets the timescale of chemical enrichment, and it is a reference element in abundance ratio that are measured and discussed in terms of their ratio with respect to iron. So it's important to understand where this iron comes from and how the enrichment with iron in the universe happened. Now, iron in the local universe is predominantly synthesized in type 1a supernovae. So this actually then led to the interpretation of the trend that's observed in the ratio of alpha over iron elements, and you see that this bends down at some point, and this knee is associated to the onset of type 1a supernovae, because they then actually contribute more to the iron production, and so we have more iron in the universe after type 1a supernovae kicked in. Now, what fraction of iron is made in type 1a supernovae? This can be roughly estimated by assuming that we have, as we saw in the morning by the results of the Lick Observatory search, 1 in 4 supernovae is a type 1a. And type 1a supernovae, as we also discussed this morning, and we know now with direct gamma measurements, they produce about half a solar mass of nickel-56 that then decays to copper-56 and iron-56, so half a solar mass of iron is produced per event for type 1a supernovae. Now, Vokalov supernovae are more frequent, but they produce much less iron. They produce about 1/10 of the solar mass of iron. So that actually gives you a rough estimate of about 2/3 of the iron in the local universe is made by type 1a supernovae. Because, of course, that was not always the case before type 1a supernovae associated to the explosion of low mass stars. Before they actually became active, and that of course happens only later because the evolution times are longer and delay times between star formation and supernova explosion for type 1a supernovae is longer than for core collapse supernovae. So before that happened, of course, the core collapse supernovae were the main source of iron. All right, now the perhaps most prominent application of type 1a supernovae, of course, is type 1a supernova cosmology, and Sylvia assigned me the task to also say some words about type 1a supernova cosmology, although this is not really my research topic. So I'll try to say something reasonable about this. Type 1a supernovae are used for distance measurements in cosmology. This is, of course, an important task for observational cosmology. Distance determination for nearby objects can be done with parallaxes or Cepheids. But if we actually are after larger distances throughout large parts of the universe, we need brighter objects. And of course, as we discussed this morning, type 1a supernovae are very bright. They are among the most bright explosions that we have in the current universe. So therefore, doing distance measurements on the basis of type 1a supernovae seems to be a natural choice. The other aspect that we also discussed this morning is homogeneity. This inspired to use type 1a supernovae as distance indicators. Now, the very rough picture, very schematic, is the following. If we observe a nearby type 1a supernova and know its distance, then we can infer its magnitude, its absolute magnitude, or its intrinsic brightness. And if we then observe the same object at a larger distance, then it appears fainter because it's further away. And this is a measure of distance, and that's then the luminosity distance. We'll actually look into this a bit more in detail later on. So this is not really working here. Maybe it's blocked too much here by the screen. Okay. Okay, now these measurements were done in the 1990s, and what was found then was that for very distant objects, that they are even fainter than what would have been expected in a freely coasting universe. Now this was, of course, an important finding, and in order to appreciate that, we probably need to have a closer look into what's behind this cosmology and cosmological world pictures. So let's do a very quick general relativity recap. So as stated by general relativity, the assumption is that the universe on large scales can be described by Einstein's equations of general relativity as given here. So this is the famous, these are the famous Einstein's equations. They connect the geometry of space-time to the sources of gravity. And the geometry of space-time is the left-hand side of Einstein's equations here. The geometry is expressed in terms of the Ricci tensor and the scalar curvature and the metric. And on the right-hand side, we have sources of gravity. So this actually is the energy momentum tensor, T mu nu, that actually contains all matter and energy we have in the universe, and there is the possibility of a cosmological constant that can also be added to Einstein's equations. Now, this cosmological constant was originally introduced by Einstein to allow for static solutions that back then were deemed to be the correct solutions of cosmology. But then, of course, with the measurements of Hubble in the late 1920s, it became apparent that there is a linear relation between the distance to an object and its receding velocity. So this is actually what Hubble measured. He measured distances to objects, to nebulae, which are, of course, distant galaxies, and determined their apparent receding velocity by measuring redshifts. Now, of course, this then implies that the universe is expanding and that we had a beginning of this expansion in a Big Bang. The age of the universe that can be inferred from this and the expansion history, of course, need not to be linear, so this is just a local measurement, so therefore they depend on larger scales on the cosmological world model. Okay, now cosmological world models in general are solutions to Einstein's equations of general relativity under the assumption of validity of the cosmological principle, which states that at sufficiently large scales, if we average structure in the universe over sufficiently large scales, then we can then assume homogeneity and isotropy. And if this is actually true, then the geometry of space-time can be described in the Robertson-Walker matrix as given here. So we have then high symmetry that is actually reflected in this form of the metric. And here we have an important parameter in the spatial part, and this is A of t. So this is the scale factor, and the k here is the curvature parameter that decides on the geometry of the universe, which could be flat, closed, or open, depending on k being 0, 1, or minus 1. Now, if we combine this Robertson-Walker metric with Einstein's equations, one gets the Friedman equations, and these Friedman equations give us the first and the second time derivatives of the scale factor as here. So the first derivative is then sort of the Hubble parameter squared, that's the first derivative squared, and this is given in the first Friedman equation, and then we have the second Friedman equation that gives the second time derivative. Now, an assumption that enters here when one actually derives these Friedman equations is some assumption on the equation of state of matter in the universe or the material in the universe. So this is assumed to be a perfect fluid with a density and a pressure related by this equation of state as given here, with P being proportional to the density with a proportionality factor, the parameter W. Now, this W, depending on what kind of cosmic fluid we have, could have different values, and if W has a value that's smaller than minus 1/3, and if this cosmic fluid with this W smaller than minus 1/3 dominates the pressure, then the second Friedman equation will tells us that the universe is bound to accelerate. Now, according to the Friedman equations, as stated here, we have a number of parameters in here. The expansion history of the universe is determined by 4 parameters, and this is the density, the pressure, or equation of state parameter, the cosmological constant, and the curvature parameter. Now, of course, it is one of the tasks, or the main task of observational cosmology, to determine these parameters. And the first attempt in this direction was made by Hubble, who did local measurements and measured H0, so that is the Hubble parameter in the local universe in 1929, and the local parameter is then called the Hubble constant. But of course, on larger scales, the Hubble parameter may depend with time if any of the four parameters in the Friedman equations is time dependent. Okay, let's first consider a universe without a cosmological constant. Then, from the first Friedman equation, one can write down a critical parameter for the density, so that we have a flat geometry. So if the density takes this value here of the critical density, then the first Friedman equation tells us that the geometry of the universe will be flat. And this defines the density parameter, omega m of matter. So rho, the density of matter in the universe, is then given as its ratio to the critical parameter for a flat geometry. And one can actually introduce similar density parameters for other components of the universe, and then rewrite the first Friedman equation in this form here, that we have h squared given as the square root of these components with the corresponding powers here. The components that are considered here are radiation, matter, curvature, and cosmological constant. Radiation can be estimated. The density parameter of the radiation can be estimated because radiation is mainly cosmological microwave background, so this is very low, and we get a density parameter of 10 to the minus 5. So this can be neglected, and therefore is usually not taken into account in this Friedman equation. In total, one should have that all these density parameters sum up to 1. Okay, now the goal of observational cosmology is to determine the size or the values of these different contributions locally, and this then would then give us information on the expansion history and the future of the expansion or future development of the geometry of the universe. Now, for that, one tests the geometry of the universe, and this is done by measuring distances and redshifts to astronomical objects. So redshift, of course, as you know, is determined from spectral observations. It's related to the scale factor, as 1 plus redshift is a 0 over a, so it relates directly, so this here directly measures the scale factor. Now, the other quantity we want to measure is the distance to an object, and if we have an object of known intrinsic luminosity, one can determine its luminosity distance. And this is defined by the flux that's measured from this object, that's defined as the known intrinsic luminosity divided by the luminosity distance squared. So in an expanding universe, this luminosity distance depends on the growth of the scale factor, and therefore also on the Hubble parameter. Okay, now, so this is what we want to measure. We want to measure redshifts. That's easy. That can be done from or relatively easy. That can be done from spectral observations. And luminosity distances. Now, luminosity distances in astronomy are usually not given and not measured directly as these luminosity distances, but in terms of distance moduli, which are defined as here. So the distance modulus to an astronomical object is the difference between its apparent magnitude, the directly accessible astronomical quantity, minus the absolute magnitude of the object, the absolute brightness of the object, and this relates directly to the luminosity distance. So determining these distance moduli is a way of measuring the luminosity distance. Now this is actually done for type 1a supernovae, so this is why they are important. They are used to test world models. So one compares for type 1a supernova measurements the obtained relation between distance moduli and redshifts with what world models predict. Now this relation, of course, is the Hubble diagram, and here's the Hubble diagram of supernovae from the review of Guber and Leipengut. Actually based on a huge number of type 1a supernova observations, and this is here in the lower part. So this is the distance modulus versus redshift, and in the lower panel the residual to a lambda CDM cosmology is plotted. Okay. Now we compare these measurements to world models. So what world models could we imagine? Well, an empty universe would expand linearly. If if the universe is filled by sufficient amounts of gravitating matter, then of course we would expect that this expansion of the universe would slow down, and it would stall if the density parameter is equal to 1. In a matter-filled universe with a density parameter larger than 1, then we would even expect a reversal of this expansion and a recollapse. So these world models are connected to geometries of space-time and also imply different ages of the universe. So this is illustrated here. We have this Hubble diagram. So this is time, this is redshift. in the end, time corresponds, of course, to distances to astronomical objects, and whatever was measured by Hubble is sort of the local relation that appears linearly. But of course, if we measure larger scales, then depending on the world model that is realized, we would expect a different shape of these world model predictions. And here we have the case of an empty universe with a linear expansion. We have the case where omega matter is 1, so that the expansion stalls, and we have the case with a omega matter larger than 1, where the universe is closed and recollapses. Now, the measurements that were done for type 1a supernovae are placed on this side here of the Hubble diagram, and they don't correspond to any of these world models, and they can only be fitted by a world model that is accelerating. So this was found in the very well-known measurements of that were published by Rees et al. And Perlmutter et al., the measurements of the HiZ team and the Supernova Cosmology project, and they found that supernova distances are inconsistent with any universe that is dominated by a gravitating component. They can only be fitted in a world model that involves a cosmological constant, and the expansion is not slowing down, but instead it is it's not slowing down or reverting, but instead it accelerates. And of course, this was defining, as you all know, that was rewarded the Nobel Prize for. Now, the important implication is that the universe cannot be filled exclusively with ordinary matter or energy, because these would act as sources of gravity and would be attracting. There must be an additional component that is driving the universe apart, which could perhaps be a cosmological constant, although this doesn't say much about its nature yet. So the nature of this component is unknown, so it was termed dark energy. But from supernova cosmology measurements, supernova distance measurements, we know that it makes up about 70% of the energy density in the current universe. Of course, determining the nature of dark energy is one of the great challenges to modern theoretical physics. And from the perspective of type 1a supernovae, of course, it is well possible that making these distance measurements of type 1a supernovae more precise may help. So the current status is shown here. So this is the omega matter, omega lambda plane with the different cosmological measurements determining these parameters. So we have cosmological microwave background here, baryon acoustic oscillations here, and type 1a supernova distance measurements in these blue circles. And as you see, these measurements are complementary. If you take either two of those, they will more or less fix a certain combination of omega lambda and omega matter, and this is what we actually have as the current parameters, cosmological parameters of our universe. Now, an interesting quantity that one wants to determine in observational cosmology is the value of the equation of state parameter of the dark energy component. Current observations are shown here, and they are consistent with a W of -1, which would correspond to a cosmological constant. And as you see here, type 1a supernova measurements play an important role in that game. So this is W versus omega matter. And the baryon acoustic oscillations and cosmological microwave background don't constrain this very much, so they actually are rather degenerate, and type 1a supernovae actually help to break this degeneracy significantly. So therefore, these are important probes for observational cosmology. Another question, of course, is then whether W is a constant in time or whether it evolves in time. Is it a cosmological constant or something that really changes its nature? So all this, of course, is a goal of observational cosmology with type 1a supernovae, and in order to improve the measurements, we want to actually make type 1a supernovae precise distance indicators. Now, in principle, as described for now, the distance measurements rely on the assumption that we somehow know what the intrinsic brightness of a type 1a supernova is. So that means that we need somehow, here's an eye missing, independent knowledge of the absolute magnitude of these objects. And this would be easy if type 1a supernovae were standard candles, and sometimes it is actually loosely stated type 1a supernovae are used as standard candles, but this is a sloppy use of the word, because if you actually look closely into the sample of type 1a supernovae, and I've shown this plot already this morning, then it is apparent that there is not really a very strict homogeneity in this set of objects. We have different subclasses. We have the inhomogeneity of the class of type 1a supernovae, and this, of course, contradicts the view of type 1a supernovae being standard candles. So there's quite a variation of brightnesses of these events. Of course, one could argue that the faint subclasses are uncritical because these are the ones that you will not see for large distances anyway, so they are not actually in the cosmological sample. The brighter events are more critical. In principle, a spectral identification would be necessary to sort those out. The brighter events that do not really follow the relation that's used to calibrate type 1a supernovae, but this is difficult because for the very distant objects, of course, spectra, high quality spectra are usually not available. The only argument that you can still then make is that peculiar objects are rare, and therefore what you observe most are normal type 1a supernovae. But overall, you could say, well, type 1a supernovae are not standard candles. So there's a significant variation even among normal type 1a supernovae. So the peak brightness varies by about an order of magnitude, and this would actually introduce large errors in the distance, cosmological distance measurements if they were not corrected for. So this is shown in this very often shown plot of supernovae from the Calantololo type 1a supernova search. So these are all nearby supernovae to which we actually know their distances and therefore can give the absolute magnitudes. These are light curves of this sample of nearby type 1a supernovae, and you see that the brightness actually varies for more than a magnitude or so. But there are calibration methods that are based on observed correlations between the peak luminosity of these objects and other observables. And of course, the most prominent of these relations is the relation between the peak luminosity or the peak magnitude in the B band and the shape of the light curve. And this was already pointed out in the late 1970s, and then Mark Phillips worked hard on making this relation a very precise relation that can be used to calibrate type 1a supernovae. So he actually cast this relation in a relation between the peak magnitude in the B band and the decline rate in the B band 15 days after peak luminosity. So he measured from the peak luminosity to 15 days thereafter, and this is then the decline rate delta M15. And he found that there's a rather tight relation between these two quantities, and this is then known as the Phillips relation or the width luminosity relation. There are other methods as well. So actually the group that produced this picture here uses a light curve fitting. So the shape of the light curves is fitted with an overall stretch parameter. So supernovae light curves are stretched or compressed, and this actually then fits these fainter and brighter events. But in the end, what's behind this is a similar relation that the peak luminosity is related to the width of the light curve or the shape of the light curve. Basically, the brighter a type 1a supernova is, the wider is its light curve. There are, however, also other important relations, and one of these is the relation between the peak magnitude and V band and its color. So brighter events are observed to have usually bluer colors. And this actually also enters the calibration methods. Now, the problem with this calibration of type 1a supernovae as distance indicators in cosmology is that this is an observational finding, and it relies on observations of nearby type 1a supernovae. So all these here are nearby type 1a supernovae to which the distances were known independently, and therefore one could actually establish this relation between the peak luminosity, the peak magnitude, peak absolute magnitude, and the decline rate in the B band. Of course, this then raises the question of whether there are any evolutionary effects. Of course, going out to larger cosmological distances, it is now clear that the same relation must hold there as well. The only the arguments that are usually made in favor of the validity of this relation also for cosmological measurements is that when one applies the corrections, then this reduces the scatter in the type 1a supernova Hubble diagram. But there's no real theoretical foundations from the side of modeling for this relation to hold yet. So therefore, uncertainties are added by the unknown nature of the origin of this width luminosity relation to the other errors one usually has in cosmological measurements, which are statistical errors, but these are small with the latest rather large samples of type 1a supernovae that involve hundreds of objects, so statistical errors are subdominant. But there are, of course, systematic errors due to the use of different telescopes, background subtraction, selection bias, reddening by dust, gravitational lensing, and so on. So there are all kinds of sources of systematic errors, but the validity of this width luminosity relation adds another uncertainty to these measurements. So therefore, the tasks for theory to support type 1a supernova cosmology would then be to provide a theoretical understanding of the width luminosity relation, and even better, if possible, make suggestions for an improvement of the calibration to make type 1a supernova cosmology distance measurements more precise. The other task would be to provide some methods for exclude or treat evolutionary effects if there exist any. So, for instance, one could imagine easily that there's a dependence of the properties of type 1a supernovae on the environment, on the metallicity, on the environment, cosmological environment in which they explode, for instance. And of course, there is the possibility that actually type 1a supernovae, supported by the fact that we see so many different subclasses, are perhaps not even one single explosion mechanism or progenitor scenario, but they actually are explained in different scenarios. So what would then be the effect of this on the width luminosity relation? So one could, for instance, imagine cases where the relative frequency of the different explosion scenarios and progenitor channels contributing to type 1a supernovae would change with cosmic age, and if there are slight differences in the properties that actually may introduce systematic shifts in the measurements. Okay, so this is actually why we are interested in type 1a supernovae, why we want to model these objects. And then the question, of course, comes up, do we actually need better models than we have at the moment? Now, the focus of this lecture will be on the theoretical modeling of type 1a supernovae as thermonuclear explosions of white dwarfs. And then, of course, if we ask the question, do we need better models, the first question would be, what is actually a better model? What is a good model? And there are actually in the community of type 1a supernova modelers quite different opinions about this. So one line of thought would say, well, the best models are the ones that fit the observations best. Other people would perhaps rather say, well, we want to have self-consistent descriptions of the physical effects. And this actually is then a better model that gives a more comprehensive understanding of the physics that gives rise to the explosion. And then, of course, one could also say, well, we don't care about the overall larger picture. We actually pick out a specific physical process and investigate this in detail and make its modeling as exact as possible. So these different approaches exist, and they are actually connected to different ways of modeling type 1a supernovae. So one first approach to modeling thermonuclear supernova explosions was with one-dimensional models. Now these one-dimensional models have the advantage that actually they fulfill the first of these points here best, so they actually provide the best fits for the observations. They're based on the assumptions of spherical symmetry, and therefore, as we will see later in this course, the physics of thermonuclear burning is not consistently captured. So we have three parameters here, and because we cannot actually consistently model all the underlying physics of how the thermonuclear burning in the white dwarf proceeds, and these three parameters are then used to tune the models to resemble astronomical data of type 1a supernovae. This was actually done in the 1980s and also in the 1990s, and still today some people produce one-dimensional type 1a supernova models. They are very successful with being tuned to resemble astronomical data. So they actually are successful in reproducing many, but not, if you look in detail, all aspects of the observables. And a prominent example of this, so the classical type 1a supernova model, is the famous W7 model of Kanemoto, 1984, and Friedrich actually also contributed to this by doing nuclear synthesis post-processing. So this is a famous example. Now it's quite surprising, actually, if you think about it, that this provides such a good fit to astronomical observations, because the way W7 was constructed and originally intended was that it was tuned to fit the near maximum light curves of typical type 1a supernovae. But still, it also provides good fits to spectra and to other kinds of observables that were taken of type 1a supernovae only later. So therefore, it has formed the basis of analyzing and interpreting observational data for more than 3 decades now. So this is a hugely successful model, and it has been applied in calculations of galactic chemical evolution. So this is a standard model that's quite often used there. It has been used in simulations of supernova remnant formation, and it actually is the basis of modeling the chemical stratification in type 1a supernova ejecta as inferred from spectral sequences. We will discuss this later on in more detail. So one-dimensional models are quite successful. However, they also have a significant drawback, and this is because of the three parameters that, of course, are good to fit into observations. They lack predictive power because you have the freedom to choose this parameter or set these parameters arbitrarily. Nonetheless, they have formed the standard over more than 2 or 3 decades, and still you could also argue that with these parameters you get at least some idea of what global quantities in supernova models would be. So these one-dimensional models make assumptions on how the thermonuclear burning spreads through the white dwarf star, and this is of course artificial, but in the end, in an overall picture, you should actually get the same or about the same speed of spreading thermonuclear flames over the white dwarf star in more sophisticated multidimensional simulations. Now the other approach to modeling type 1a supernovae is what you could perhaps call predictive models. So here, the intention is a detailed study of the physics that goes into type 1a supernovae, and if we actually if we aim for a consistent description of the physical effects, then we have to diverge from spherical symmetry. The fundamental processes, as we will see, involve intrinsically multidimensional hydrodynamical effects. So this requires multidimensional explosion models, and the development over the last, well, it's not so recent anymore, over the last maybe 10 or 20 years has been that people have constructed 2- and 3-dimensional simulations of explosions, of thermonuclear explosions of white dwarfs, assuming in 2 dimensions axisymmetry, or in 3D no symmetry at all. Now here, the goal is, or the intention is, that we want to model the physical processes by avoiding the 3 parameters as much as possible. We'll discuss later on to which degree this was possible so far. So that means that we fix the description of the models so that the ingredients, the physical mechanisms are described appropriately. But that also implies that we don't have tunable parameters anymore, which is good, of course, if we want to understand the physics and if we want to make predictions, but this is bad if we want to fit observations. So these multidimensional models so far are not doing so well in fitting or matching the observations in detail. So if you actually show the predictions of spectra from multidimensional models that we are proud of producing to people who actually model stellar spectra, they would always say, oh, this is a horrible fit. How can you say this is actually a success? Because, I mean, the standard there is rather different. These multidimensional models are certainly less suited for the analysis of astronomical data. However, they may give a better physical explanation of the observations. Now, in all ingredients that go into modeling type 1a supernovae, also in multi-dimensions, we have the evolution of the star and the supernova and the explosion and then the formation of the remnant, and all these aspects have important aspects that are unclear from observations and elusive from observations, and therefore the observations alone cannot actually determine the physics that goes into the evolution of the progenitor, the supernova explosion, and the remnant formation. So we have to test this with predictive models. And a prominent example of this problem that we have to address here is the type 1a supernova progenitor problem. We don't know what the nature of the progenitor system is, so one idea then would be that we assume different possibilities and calculate the explosions of these objects, derive synthetic observables and compare to the observations, and then the hope is that in this way we can assess the validity of our assumption on the progenitor star. The main result so far is of this multidimensional modeling approach that they allow to study different such possibilities, different progenitors and explosion mechanisms in quite some detail with huge with extended numerical simulations, and it seems that at least some of them, or a variety of them, contributes to the overall sample of type 1a supernovae. So the suggestion at the moment is that type 1a supernovae indeed are not explained by one single progenitor evolution channel and a single explosion mechanism, but a multitude of these possibilities contribute to the observed sample. Okay, so the ultimate goal of type 1a supernova modeling therefore would be to understand in detail the explosion mechanism, the connection to the progenitor structure and evolution, the nucleosynthesis processes that go on in type 1a supernova explosions, the formation of observables, and the evolution of these objects into the remnant phase. Almost all that goes into this, as said before, is afflicted with considerable uncertainties. One exception from that rule is perhaps nuclear physics. The nuclear physics input also, of course, is not free of uncertainties, but these uncertainties are small compared to other problems we have in modeling type 1a supernovae. Therefore, a wrong assumption in any of these ingredients in the models could easily lead to could completely destroy the model and could lead to wrong conclusions on the validity of the overall supernova model. So these are the ultimate goals. The more practical goals for current type 1a supernova modeling are to construct, first of all, one of the nuclear supernova model that matches at least observables of a certain subclass in detail. Then this model should also quantify the realization frequency of the different progenitor channels, or say why actually this particular channel is frequent or rare. We want to determine the detailed nucleosynthesis yields of these particular subchannels that are described with the models, and both aspects, the realization frequency and the nucleosynthetic yields, are necessary to quantify the contribution of type 1a supernovae as a source of galactic chemical enrichment. And of course, then in the end, what we also hope to be able to do someday is to determine the origin of the width-luminosity relation and other relations that are used in type 1a supernova cosmology, and to use this knowledge to improve the precision of these observations. Now, the challenges in type 1a supernova modeling are the progenitor problem, as mentioned before. So the pipeline that's currently constructed is that we assume a progenitor structure and then model the explosion and predict observables and compare to astronomical data. And this is then hoped to be to give you some idea of how valid the assumption on the progenitor structure was. But there are, of course, problems with this approach. And the problems, first of all, is that it relies on a consistent and parameter-free modeling of all explosion and observable forming processes. So all this progenitor, so the progenitor is assumed, and then we predict observables and compare to the observations. But that means if we want to have draw firm conclusions, then all this these steps in between the explosion model and the formation of the observables have to be understood without free tunable parameters. There has been progress over the past years with multidimensional simulations of type 1a supernovae, but not all parameters are fixed. So there is still some unknown physics, for instance, in some of these scenarios that, for instance, involve deflagration to detonation transitions. We will discuss this in more detail later on. And there is also a limited resolution of models that forces us also in these multidimensional simulations to introduce modeling of physical effects that also sometimes then involve, again, parameters. The next step is, of course, the comparison to the observations. This is also not as straightforward as what one might hope. So the first question here is how telling is actually the observational data we have of type 1a supernovae for constraining the explosion process. In the end, of course, we don't actually have an experiment where we can make measurements to determine specific mechanisms, but we have to live with what nature provides us with, and these are observations. And it's not clear that they really test the explosion mechanisms without any degeneracy. And as we will see, there are actually models that predict that are very different in their physical nature, but predict very similar observables. So there is quite a bit of degeneracy in models to explain the observational data. The question is then, how can we break this degeneracy? Then, as mentioned before, we have only a limited ability to exactly reproduce observables with our multidimensional models. So the spectra look similar, but they are no perfect matches. So then, of course, the question is, if we have an imperfect match with an observed spectrum, what is important in this part? So should we actually then judge the quality of the fitting of the observables with a model based on a single line or a line velocity or something like that? So this is hard to decide. And of course, the models that we do, the multidimensional simulations, are rather complex, and so therefore it's very hard to estimate the errors that we have in the models if we want to then compare to the observations in detail. Okay, so finally, the personal view on all this is, I think that multidimensional modeling of type 1a supernovae is the way forward to explain type 1a supernovae, even if one-dimensional simulations fit the data better, because the goal here, at least from my side, would be to understand the physics that's behind type 1a supernova explosions, and therefore the physical processes should enter the model as realistically as possible. So therefore, the focus of this course will be, if we then talk about explosion simulations, on recent multidimensional modeling approaches, and this will be explained and surveyed together with some basic principles of type 1a supernova physics and the numerical techniques that are necessary to perform such simulations. So this is actually what I want to finish the introduction with, and this is what we want to aim at this course. Thank you very much for your attention.
Despite of the fact that you said that there is no any theoretical foundation for Witt's luminosity relation, there should be some explanation. Could you mention?
Well, I mean, of course, people are trying we're trying to derive synthetic observables of the models, and then of course we test whether they actually predict something that goes along this with luminosity relations. And there have been actually cases where this seemed to be successful. But the problem is that this with luminosity relation is very hard to model in detail, because this delta M15, at least that's what my colleagues doing radiation transfer calculations of type 1e supernova tell me, that this delta M15 is very hard to determine, because the current picture behind this is that this depends on the evolution of the ionization structure in the ejector. So this actually is rather complex to model. So you have to actually do non-LTE physics there in quite some detail. And this is actually very hard. So people, my colleagues who work on the determination of observables always tell me, well, this delta M15 is a horrible quantity actually to nail down with theoretical models. So therefore, this seems to be rather hard. And yeah, I mean, of course, there are some ideas what actually could give rise to such a with luminosity relation. This is actually a change in the thermodynamic structure, in the ionization structure of the ejector, but this is rather complex physics and not well understood in detail. There's input data missing. There's not all atomic data available for this, and the modeling of the physics in multi-D radiation transfer is very expensive and very hard.
There's a second question.
Yeah. Okay.
Another question, maybe? We will switch to